Okay?
That's $20.
So that's what you want to look at. So here's your list. CnNO2, notice that's NO2, not NO3. The fluoride ion, the water, and Cl minus. So you want this from being the strongest base to the weakest base. So basically, no pun intended, what am I asking you to arrange it based upon the ability to do what?
Steel hydrogen.
Take in a proton, right? Okay? That's it. So, right away, which one do you think is going to be the most unwilling to take in a proton?
Cl.
Cl minus. Why?
Conjugate base of a strong acid.
This is conjugate. So this has no desire whatsoever. This is going to be a horrible base. Okay? Now remember, water is like a tipping point. So if you put, for example, C2H3O2 in water, is that going to ionize?
No.
No, why?
It's clumpy.
It's weak acid. This wants to stay umpy. Can I say umpy?
Umpy sounds worse.
It really does. Humpty Clumpty? And the crowd boo. Okay, so here's the story. The water in this situation is not going to be able to take away a proton. But if you put hydrochloric acid in water, can water take away the proton?
Yes.
So in this case, water acts as a strong enough base because it's a tug of war. So on a visual, understand there's two things vying to hold on to that proton. There's the chloride ion trying to hold on to it, and there's the water. If it is a strong acid, who wins, the water or the anion?
Water.
The water does, which is why it ionizes into hydronium ions and fluoride ions. If it's a weak acid, then what?
The anion wins.
The anion is stronger, and that's why it doesn't dissociate. So water is like a tipping point, okay, between a strong acid and the weak acids, okay? So you'll notice on this, what do you notice about all of those remaining ones? Or they're all conjugate bases off of what?
Weak
acids.
Weak acids, okay? So these are all conjugate bases off of weak acids. So these at least have the capacity to be a decent base because these are the conjugate bases off of weak acids. Now, what mathematical number could you look at to try and figure out which one is going to be the strongest base? Would you look for big Ka values or small Ka values?
Small Ka.
Small Ka value. So the one with the smallest Ka value is going to be the best conjugate base. So if you look at these, let me give you the numbers. So fluorides, its Ka value is 6.8 times 10 to the negative fourth. The NO2 is 4.5 times 10 to the negative fourth, and the hydrocyanic acid, that Ka value is 4.9 times 10 to the negative 10th.
That's
Okay.
the strongest.
So by far and away, when you see this, what do you notice about that Ka value? It's extremely low. So Charles, since you have a really, really, really small Ka value,
Have a really, really, really big KB value.
strong
base.
So it's going to be a strong base. So the Cn is going to be the most willing to take in a proton. Okay? So this Cn is going to be the strongest base because it has the smallest Ka value. Now, if you follow that thought process through, you're comparing the fluoride ion to the NO2. Which one of those has the bigger Ka value?
The nitrite.
The nitrite or the fluoride? Which one has the bigger Ka
Oh,
value?
bigger Ka, my bad. Fluoride.
Fluoride has the bigger Ka value, so therefore it has the weaker base. So which one of these two has the stronger base?
Nitrite.
The NO2. So your sequence is actually just like that. That is the sequence. Okay? Because your Cn minus has the smallest Ka value. So when you rank these, and I promise you, you're going to have a question like this on the test. I promise you. Okay? And I'm going to give you the Ka values. And water is going to be in there. I promise you. Water is the break point. Now, I won't do this because I'd be an absolute jerk. What if I put water, nitrate, and chloride and fluoride? Could you rank them? No?
No, because
What?
nitrate and chloride are both.
Both of those are conjugate bases off of, so they're both equally horrible, okay? So you couldn't actually rank them because you can't compare the nitrate to the Cl minus. Okay, one last problem and then I'm done. So let's say I gave you this problem. Moles.
Oh, no.
It's not that bad.
Probably not. I just don't think it's
Easy going, Chuck.
on what is coming. I think it shouldn't be too bad. Right?
Nope.
You have the pH. You can
Okay.
isolate it.
So, how many moles of potassium fluoride should be added to 200 milliliters of a 0.1 molar solution of hydrofluoric acid to produce a pH of 3.5? You've got the Ka value. So if you have the Ka value right away, what can you find?
pH.
Oh, I can't find the pH.
PKA.
I can find the pKa, right?
Use hacky sack.
So look at this. pH equals pKa plus the log of your anion concentration over the concentration of your acid, right? You know what your pH needs to be.
Yep.
Got that number. Can you find your pKa?
Oh, and then
That's
you
actually
can
not
just,
bad.
that's just,
Because
that's
then you do,
easy.
because then you put it to the
Algebra.
to the 10.
Oh, it turns into a math problem.
I
It's
can do
always a
math problems.
It's always a high.
Math problem is the one.
I don't know, we'll see if we can,
Okay.
we'll see what happens on the physics. I'm really not a bit confident about that.
I'm a one-trick
Okay.
pony, it's math.
So,
Stupid
somebody
English.
take the negative log of 6.8 times 10 to the negative
I can't
4.
read. That can't hurt
Can't
me.
articulate.
That can't hurt me because I can't read.
3.17.
3.17? Okay.
Oh, that's-
So, I want, now, before you do anything else, okay, do not touch a calculator, do not do algebra, do not do anything.
What?
He's gonna check this concentration.
Do not touch a calculator.
Would be wrong.
Which one has to be the bigger concentration, your anions or your acid?
Anions.
Why?
Bigger than one.
Because I need to take the log of a number bigger than, so that I can add that to 3.17 and get So right away, I know my anion concentration has to be bigger than the concentration of my acid. Okay? Now, you know what your pH is. Got that number. So, and I even know the concentration of your HF. So what's the only thing you don't know? That anion. So basically this initially is an algebra problem. So what's the first thing you need to do to get the anion by itself? So I'm going to subtract 3.17 and get
Whatever that is. What's that?
0.33?
Yeah.
Like the base 10 of that.
Okay? So how do I get rid of the log? Now, do I take it 10 to the negative 0.33 or 10 to the positive 10.33?
Positive.
Why? Because this isn't negative log. Okay? It's just normal log. Okay? Such as normal log could be. So, I'm going to take 10 to the 0.33 is going to equal my anion concentration divided by my HA, and I know my HA is going to be 0.1 mole. So somebody take 10 to the 0.33 and multiply that by 0.1.
That's 0.21.
What'd you get?
0.21.
How about one more decimal place?
0.214.
0.214. Now, what units is that in?
Polarity.
It's in molarity. Is that what you want?
No.
What do I want?
Moles.
Ooh. Ooh. So what do I do?
Times by liters.
Ooh, you know what the volume is, right? Because this means 0.214 moles per
Liter.
1 liter. Do I want 1 liter?
No.
What do I want?
0.2.
0.1. So what am I going to do? Multiply that by the volume, which is 0.2 liters. The liters cancel out. You're left with moles, and you get whatever that is. 0.0428 of potassium fluoride. Now, if I ask you to actually measure out the grams, what would just be your next step be? Yeah, just multiply that by the molar mass of potassium fluoride. Okay? Got it? Good, Grant? Okay, stop you on the camera.
No homework.
Oh, Lord, no.